Okay. I think I'll minimize that. And okay, chapter 1. Our authors call it chemical foundations. You got to start someplace, and this is it for chemistry. Chemistry is, in its simplest and broadest terms, an explanation for what we see in nature. It's how do substances, we try to explain how substances change from one form into another. So this substance has a given identity. It has characteristics that are unique to that substance, but if it undergoes some kind of change, it becomes some other substance, and then we have to explain why that happens. Let's see, Stanton. There we go. Let's see, take a quick gander here. All right. So in order to do that, the chemical world is so small that actually most of what happens in chemistry we can't see even with a microscope. But we use the term microscopic because of the limitations of our language. And it's easier to say that than submicroscopic, because most of the things that happen in chemistry happen under the radar, so to speak. You can't see them. So we've got to try to explain what's happening to the microscopic world in terms of the macroscopic world. What can we see? What can we measure? And then devise a reasonable explanation for that. Another way of saying that is nature just does what it does, right? Rain falls, forests burn, whatever else may happen. And our job as scientists is trying to explain why that happens, right? Nature could care less. It just does what it does. So when we try to devise descriptions and explanations for things that are happening in the chemical world, it's often useful, if not instructive, to think of these things in terms of the atomic world. Get yourself down to that level. Okay. So speaking of atoms, right? What does atom mean anyway? I think words just usually, I should say, words usually just don't appear out of thin air. You know, unless you're in the hood and somebody makes up something and everybody says, okay, that sounds good, let's use it. But in sciences, the words mean something. And they're usually derived from either Greek or Latin. Well, atom is derived from a Greek combination of Greek words. The root word, TOM, comes from the Greek for tomos, which means to cut. And A is the prefix that means not. So not cut is an atom. And what that means is that the atom is the smallest part of a substance that you can get and still retain the properties of that substance. And in fact, that substance is an element. So that's the smallest part that retains the properties of the element. So then once you have atoms, and each element has a different atom. So oxygen has an atom that has a certain has certain characteristics, and hydrogen has certain characteristics as the atom. When you put them together and in a certain configuration, you get a molecule. And a molecule is a combination of two or more atoms. They can be the same or they can be different atoms, but they behave as one. And another way to say that is this atom has characteristics, this atom has characteristics. When you put them together, the molecule has characteristics that are completely different from either of the other two. And the example here is water, composed of oxygen and hydrogen. Oxygen is usually a gas. Hydrogen is usually a gas. Oxygen supports combustion. Hydrogen is combustible. But when you combine them in a certain way, you get water, and everybody knows water doesn't burn. You pour water on a fire to put it out. So there's one characteristic that has changed. Now this is a molecule in which you have two different elements, two different atoms, types of atoms combined. But you can have combinations. In fact, oxygen in nature usually has two of them combined together. That's normal. It's called diatomic molecule. Hydrogen's the same way. Okay, so when you react them together, like if I put it out here like that, you can get water. Now that's not balanced. We'll talk about balancing equations later. But the gist of it is combine two and get something different. All right. And this slide speaks to that thing. It's called diatomic molecules. Now, I mentioned in our first meeting, as we were doing the grand tour, that there was a periodic table which had identified the elements that I want you to memorize, the symbols for those elements. And among those were some of the elements that were characteristically, they usually appear as diatomic. So at 1 atmosphere pressure and room temperature, oxygen is one of those. It's diatomic element. Hydrogen's another. Nitrogen's another. Fluorine, chlorine, bromine, iodine, all of those are diatomic. So when you write them in a chemical reaction, unless you're told otherwise, always write them as diatomics. But they are molecules. They're hooked together and they behave as a single unit. So how do we write chemical reactions? Well, I just did one without saying why. But we generally put, not generally, we always put the reactants on the left-hand side, and then an arrow, at least a single barbed arrow, sometimes a double barbed, going that way and that way, and then products on the other side. That's our way of expressing something changing into something else. And this is how it happens. In the case of this example, which we've expanded to include pictures too, you have two water molecules, and if you put electric current through them, direct current, you can break the bonds of these hydrogen oxygens, and they reform into oxygen molecule and hydrogen molecules. Now we need to stop for a few minutes and discuss science in general terms. That was our macroscopic explanation for what's happening in the microscopic world in terms of, for our example, the electrolysis of water, the breaking of water into its component elements. Science, in general terms, is non-specific. Science is merely a framework. In fact, it's been popular in the past 10 or 20 years to try to train students to think critically. And there are various explanations for that. They're not very good. But when you have this umbrella of critical thinking, underneath it, as one category, is science. Science is a framework of critical thinking. It is a way of approaching the natural world in such a way that you can explain what's happening. Now, it requires imagination, and it requires persistence, and it always requires more than one brain acting. One person rarely makes significant discoveries on their own. They usually build on past science's work. And this term science can be tweaked slightly depending on what discipline you're in. So science in biology will mean something a little bit different than science in chemistry, and definitely means something different in science in physics. But they all follow a general pattern, a framework. It can also be thought of as a plan of action. You know, how do you best approach a problem in the natural world in such a way as to get the most information out of it. The other thing that's commonly misinterpreted in the popular culture, and definitely in courtrooms, is that science is derived from, no, that's the wrong way to put it. Science is settled. When you hear somebody say settled science in the same sentence, you know they're idiots. They don't know what they're talking about. There's no such thing as settled science. Science is always questioning its own precepts, its own conclusions. That's the nature of science. And those who think otherwise are usually trying to scam you. The most disturbing scams of all are when those that we trust, particularly in the political realm, use the argument of settled science to bully people into behaving a certain way. So when somebody says, like Al Gore says, that global warming is true and that man caused it, well, I know right away. And then, of course, in that mess of sentences that he throws together, he's saying the science is settled. Argument's over. Global warming is fact, and we better do something about it. Well, the fact of the matter is actually that there can be cases made on the other side that global warming or climate change has little to do with human activity. So the point I'm trying to make is that settled science is a myth. Science is never settled. It's always changing. It's always, true science is always open to argument and reinvestigation. And the scientific method is one way we get at that. Okay, here's a schematic of what we might consider as the scientific method. Usually the scientific method, at least at this step right here where you see observation, just prior to that or just after it is a question. Someone has seen something and it sparks their curiosity. They want to know how that happens, why that happens. So if you're not curious about anything, then you've got no business in the sciences. But the next step is to propose a reason. You know, why did that happen? Why did you think that it happened that way? You know, like the famous story about Isaac Newton and the apple falling from a tree. I don't know if it's true or not, but the story goes that Newton saw this apple fall from a tree, and he's wondering, why did that happen? Why didn't it detach and go up or go sideways? Why did it fall straight to the earth? So the next step is to propose a reason. Why do you think that happened? And the best hypothesis, right, that explanation, is the one that can be tested. In other words, you can devise an experiment that under certain controlled conditions will allow only certain things to vary, and it makes it easier to home in on an explanation. You know, is your hypothesis true? I say it happens this way because of that. Well, if you do the experiment and it doesn't happen that way, then you know that something in your experiment is not fit to the observation. Okay, so you can go round and round and round with observation, hypothesis, experiment over and over and over again. And just because you find out that your hypothesis is wrong is not a bad thing. It's like what Thomas Edison. Somebody asked him if he was disappointed that he had failed so many times to develop the light bulb. And he says, I didn't fail. I just found that there were 99 ways to not make a light bulb. All I had to do was find the one way. So negative information is just as valuable as positive information. Supportive, non-supportive, they're both valuable. They inform your selection of the next hypothesis and experiment in the cycle to get closer to the answer. Now that can go on and on by itself for a long time. And if you repeat these experiments, tweaking them now and then you may discover that some things happen the same way every time. As long as you set the conditions a certain way, then you always get the same results. And from that, we develop what we call laws. Laws only explain, they only say, this is what happens. What happens when these conditions are given? It's only when we decide to say why something happens that we can develop a theory. A theory, that's the key word. The difference between a law and a theory is why. Once you know why something happens, or you propose something happens because, why, then that broadens your horizons. Now you can change things in the model, we call it, and see how that affects the reaction of the system to your changes. So once you have a theory, you can actually start making predictions. That's key. When you know why, you can predict. And then you also can experiment. So that really left out a step here. When you experiment, you need a hypothesis to test. And that can go around. And you either confirm the theory or you fail to confirm the theory. Now, if you have a theory that works, but you come along and time again, you find situations where it doesn't work, right? So what do you do then, right? You're stuck. Maybe you're stuck and maybe you're not. So what do you do when your theory fails? In my mind, you have three options. One, throw it out, start over again, right? If it's really bad and it fails many more times than it succeeds, throw it out. The other possibility is modify it. Sometimes you can just make little tweaks to your theory, modify it, and it fits more circumstances. Typically what happens with a theory is it's modified over and over and over and over again for a long period of time. And finally it gets so complex that it's unusable, in which case you go back to step number one. The other possibility is restrict its usage. Just say, okay, it's not going to work under those set of circumstances. It will work under these, and it always works for these. We'll keep it for just these, and we won't try to use it where it doesn't work. Perfect examples are the Newton's laws of motion. Okay. First law of motion. An object in motion tends to stay in motion unless acted upon by an external force, or an object at rest tends to stay at rest unless it's acted upon by an external force. Second law, force equals mass times acceleration. If you have a mass and you apply a force to it, a constant, unbalanced force, it will accelerate at a certain rate. Just examples. Now, where does that theory, or where's those, actually that's not a theory, those are sets of laws. So I'm sort of sliding to the side here. But what do you do with them? The same problem with theory happens to laws too. Newton's laws don't work when you get close to a black hole, right? The conditions are just way too extreme. So we don't use Newton's laws next to a black hole. We use relativity, which came later and from a different scientist, a German, name is Albert Einstein. Anyway, okay. So this is one option. You modify your theory until you get it where you want it, and then somebody else can take it and use it for something else and find out whether it works or not. So here it is in print. A law is just a summary of repeatable observations. That is, this is how it happens. I don't know why. A hypothesis can test your explanation. You just say, this is my observation, my explanation for the observation, and then I can experiment to test it to see if it works. And then a theory is the next step beyond law. It says, why does this happen? Okay, in the sciences, sooner or later, somebody has to measure something. You know, think like pull out a meter stick and measure something, or pull out a balance and find out how much it weighs. When they do that, there are two components to the measurement, and they are they can't stand alone, right? You've got to have both of them. One is the number. You need a magnitude, a measure number, like 1, 2, 3, 4, 5, 6, 7.48. But that number by itself as a measurement means nothing. Like if I said I were 200, I'm 200. What does that mean? You don't know what it means. There's no unit of measure going with it. If I said I were 200 pounds, now that makes sense. I've been measured to weigh 200 of this unit of measure, pounds. So every measurement has a number and a scale unit. Sometimes, particularly if you use an instrument to do the calculation, the measurement for you, sometimes the measurement is compiled internally to the instrument, and it spits out an answer with more complex units of measure, right? Instead of just simply grams, which is a measure of mass, this case, it would spit out joules seconds. So that's joules times seconds. This is a unit of energy. This is a unit of time. And if I were to make that measurement by hand, I couldn't do it. But if I made this measurement, and on the same thing I made this measurement, and combined them, I could get joule second, or I could get a combination of measurements. So it's okay to have the combination of measurements. In this case, they're product. Sometimes they can be quotients. For instance, density. One gram per cubic centimeter, the density of water. So that's a combination. But I got that measurement by making two different measurements. I measured the volume of water, and then I weighed it. So I made two measurements and combined them into one expression. So in mathematics, you can add, subtract, multiply, divide powers of numbers. But in science, you can add, subtract, multiply, divide powers of units also. Now, the thing that scientists need is an agreed upon standard. Right? If I say kilograms to a scientist, they know what I mean. But if I say bulbos, they don't know what I mean because it's not defined. So I could say a bulbo is this big, and that scientist over there could say, no, a bulbo is this big. So we have to agree upon units of measure. And we start by fundamental units. And these SI, this is the international system, is agreed upon units of measure. These are fundamental. That is, they can be verified. And they have a standard that you can use as a scientist to compare your unit with their unit. And everybody agrees upon that standard fundamental unit, and they all compare their other units to that one. So if we're trying to determine mass, the standard is the kilogram. If we're trying to determine length, the standard is the meter. Now, up until recently, both the kilogram and the meter were physical objects, each made out of a platinum iridium alloy for minimal corrosion, and they were stored in a double bell jar with an inert atmosphere, probably argon, in a cave somewhere in France. To this day, kilogram is still there. And for historical reasons, the meter stick is still there. But now we have an alternate way to measure the meter by counting wavelengths of a certain color of laser light. So if you have the equipment, which is pretty pricey, you can set the value for the meter using that light standard. The second has been around for a very long time. So it was sort of grandfathered into the fundamental units. It's a unit of time, and it has to be standardized and agreed upon. The unit of temperature is the Kelvin. The nice thing about the Kelvin is it's the same size of unit as Celsius. So degree C and degree Kelvin are exactly the same size unit. It's just that the 0 point for Kelvin is different than it is for Celsius. Electric current standard is the ampere. We're not going to use that in Chem 1. We get to it in Chem 2. An amount of a substance, like counting. How many things are there? Is the mole. And we'll define the mole later also. Luminous intensity of the candela, we won't mess with that at all. Now, these are fundamental units, but they're not always convenient units. So we need a way to derive units. And before we get to those, you'll notice that the kilogram is a 2-syllable term, actually 3 syllables, but the prefix is kilo, and the gram would appear to be the fundamental unit. The problem with that is, well, the gram is inherited from brain freeze. Is inherited from alchemy, but it's a very small amount, right? So what happens if you have this platinum iridium cylinder and it's only that big? If you accidentally scratch it or it corrodes, then the percentage difference in its original weight is huge, and that'll never do. So it was decided we need something bigger. The gram's already here, so our fundamental unit is going to be 1,000 times that gram, like that big. The kilogram. So that's why the kilo is part of the fundamental unit for mass. Now these are our prefixes. The most important ones, these are prefixes for deriving a larger unit of measure. Right? So if we have a meter length, but we need to measure a distance like from here to Miami, Florida. In meters, that would be a huge number. So we reduce that to, we change that to kilometers, kilometers, 1,000 meters, right? Here's the kilo. So when you say kilo in front of meters, you mean the unit of measure now is not this long, but it's 1,000 times bigger. So that's your derived unit. Everybody knows about gigabytes and terabytes, storage, amounts of storage of your electronic data in your computer, right? Gigabyte used to be huge for computers. Now it's commonplace to have a hard drive in your computer that'll hold terabytes of information. Now we can get really small too. Say the unit of a meter is just way too big to measure the size of a bacterial cell. So we shrink that down to a millionth of a meter, a micro. Micro is a millionth of a meter. So this is a unit of measure that is a millionth of the size of a meter. It's very small. It's more convenient for measuring things that are microscopic. These other ones are extremely small, like the nano is a billionth of a meter. Everybody knows about nanotechnology. They put nanofibers in some of your clothes. They're measured with the nanometer as the standard. So you need to know what each of these means. And you can say 1 micrometer is equal to 10 to the minus 6th meters. Or 1 nanometer is equal to 10 to the minus 9th meters. Another way of saying that is 10 to the 6th micrometers equals 1 meter. Okay, they're both equivalents. All right. Now, we've talked about fundamental units and which applies to what. So when we measure mass in kilograms, it's the same everywhere in the universe. Well, except when you get close to a black hole, and then all bets are off. But for most of our purposes, mass is constant throughout the universe. It measures the amount of substance. Whereas weight is a force. And the force is applied depending on the size of the gravitational field. So on the Earth, I may weigh 200 pounds. But on the moon, I'm still, well, that 200 pounds, maybe 90 kilograms. On the moon, I'd still be 90 kilograms, but I wouldn't weigh 200 pounds. Right? I'd weigh closer to, let's see, maybe 33 pounds, something like that. So there's a difference between mass and weight. Now, when we talk about weighing something on a balance, we're really talking about determine its mass. So that's a historical flub that I just can't get away from. So when I say weigh it, I mean determine its mass. Okay. Here's another very important concept in sciences. Uncertainty. Uncertainty just means that when I say I have measured this piece of paper and my ruler says it's 10.9 inches. Yeah, maybe it is and maybe it isn't. In other words, I had a professor that used to say, it ain't necessarily so. He was referring to statistics. But there's always uncertainty in a measurement. Now, if you know that this paper is 11 inches, I mean, that's obvious then. 10.9, I missed it. The uncertainty in my measurement is 0.1 inches. But just recognize that anytime you make a measurement, there's always uncertainty. It could be due to the instrument you're using. It could be due to the way that you're using it. So if I'm reading volume in a graduated cylinder, it's got markings on it, and my eye is level, I'm more likely to get an accurate reading. But if I'm off, up or down, I may be reading what I think is the volume, but it's wrong. And because of that, that's got a special name. It's called parallax error. I'm not looking straight across the level of water. Anyway, we need to find a way to quantify uncertainty so that even if we can't control it, although sometimes we can minimize uncertainty, but we can never eliminate uncertainty. So we need a way to express uncertainty. And one of the ways is in how we write our numbers. We write numbers this way, and every scientist understands this. When you write a number with a unit of measure, say, if I write that number, that's a bad example. Let me use a different one. Let's say 2318.7. And let's change that to centimeters. Okay, when I write that number, any scientist understands that you're saying that one is certain. I'll stake my reputation on that one, that one, that one, and that one. Those are certain numbers, certain digits in that number. The last one is uncertain. So one way we get around, or we accommodate uncertainty, is to say, I think that's what it is, but I'm not absolutely sure. These right here, yeah, oh, definitely. Those are true. This one is, that's the uncertain digit. So that means that the last digit is a guess. Sometimes it's a pretty good guess, but every scientist knows that it's just a guess. Now, what does that have to do with taking measurements? Well, here's an example. So we took this part of this burette and expanded it. And notice that in a burette, as opposed to a graduated cylinder, the graduated cylinder marks from bottom to top. 0, 1, 2, 3, 4, or 10, 20, 30, 40, 50, from bottom to top, because the graduated cylinder is designed to contain a volume, whereas a burette is designed to deliver a volume. So it's measured 0 from the top down. Okay, and in this case, between 20 and 21 are 10 subdivisions. So what does that mean each one is worth? If you divide from 20 to 21 is 1 milliliter, and milli means 1,000th of, so the unit of measure here is 1,000th of a liter, which is a derived unit itself of volume. Then if you've got 10 divisions between 20 and 21, each one is worth 1/10 of the whole, right? So each line here is worth 1/10. So this first line will be 20.1, and the second will be 20.2. But our meniscus, the bottom of the meniscus, is between those two marks, right? So 20.1, yeah, those are numbers, those are valid numbers because there's a marking for them. But this middle one doesn't have a mark, it's a guess. I'm guessing, halfway between 0.1 and 0.2, which would be 0.05. So that's why I write the number as 20.15. Now, which are the certain ones? The first three, and the uncertain one is the last number. Okay? Now, another concept. In popular culture, accuracy and precision are used interchangeably. You'll often hear the expression, how precise is your measurement? When they really mean accurate. So the difference is, accuracy is how close does your measurement agree with the true value? If you know the true value, right? If we assume that this page is 11 inches long, then we could say that's the true value. And my measurement was off by 1/10. So it's accurate, sort of. But what if you don't have a true value? What do? Instead of the true value, how close is your measurement to the accepted value? Now, the accepted value may simply be an average of hundreds or thousands of different measurements. Okay, it's an average. And that's valid because we rarely know the true value when we're doing research. We really don't know what to expect. So the accepted value is our target. Precision, on the other hand, is when you make 2 or more measurements, how close are they grouped together? That's precision. And this is my illustration. In fact, this may have come straight out of the book anyway. We've got 3 here, but we're missing 1. Now this one, if we average all these together, where would that value be? It'd be right in here somewhere, wouldn't it? Right? If you average all these all these scores together, it'd be right in there. So how far is that from the accepted value? The accepted value is the bullseye, right? So we're way off. It's not accurate, right? We can't throw darts worth a damn. How about precision? That's not a very good grouping either, is it? So for this one, we're not accurate and we're not precise. Neither one. Whoops. Sorry. Neither accurate nor precise. How about this one? Well, that's not accurate either because the average is way out here. But we are precise because they're very closely grouped. Okay. This one is both accurate and precise because the average is very close to the bullseye and they're tightly grouped. So anybody here that's a hunter, before you head for the woods, you want your firearm to shoot true. In other words, if you look through the scope and the crosshairs are on that place out there, whether it's a target or an animal, you want the bullet to land where the crosshairs say it is. So you set up a target. And usually, most modern firearms, you fire 3 shots and they're going to end up grouped very close together, but they may not be on the bullseye. If that's the case, then you make adjustments in your scope, right? For left, right, up, or down. And you do that until you got that tight group on the bullseye. Then you're ready for the woods. Now we're missing one here. If we got neither accurate nor precise, precise, not accurate, accurate and precise, we're missing one. One that's accurate but not precise. So what would that look like? Accurate and not precise would be, let's say, here's the bullseye. You hit it around like this. The average of those is right on the bullseye. So it's accurate but not precise. All right, so we've identified our number without the units now. We're just talking about numbers. We'll put units back with them later. The expression of a number can be interpreted in terms of significant figures. That is, which ones do we need to retain if we have to manipulate that number? It's good to identify which ones are significant and which ones don't matter. Which ones are throwaway? Well, we've got rules, right? So our significant figures in a number, based on the first rule, all non-zero numbers are significant. So this number has 4 significant figures. All 4 of them are significant. The other possibility is we've got a 0 in there somewhere. And there are 3 types of zeros, right? One's in front, one's in the middle, one's behind. We call those leading zeros. Leading zeros are never significant. They're just placeholders, right? You still need them. Yeah, you still need them because if you don't have this placeholder here, if you take that out, then now the decimal shifts over here and it's 0.48 and not 0.048. It's an entirely different number, but it's not significant. All leading zeros are not significant. The other thing I will point out here is a pet peeve of mine. When you write a decimal point in front of a number, you better stick a 0 out here in front of it to the left. I don't want to see any decimal points without a leading 0. I call those, when there's no 0 out here, I call them orphan decimals. They're missing a parent. Okay, so Whenever you write those, be sure and bracket those decimals on the left-hand side. Okay, so this number only has two significant figures. These non-zero numbers and those zeros that don't count. The next type is a captive zero. That is one that is bracketed by non-zero numbers. Now, here we just show you one, but there could be a whole host. You could have 3 or 4 or 5 zeros in there, place-holding positions, and all of those zeros would be significant. They would be trapped between two non-zero numbers, and we count them as significant. The other possibility is zeros to the right, trailing zeros. Those can be significant, but not always. So when are they significant? Whenever there is an explicit decimal point in the number. This one has a decimal, so that makes these zeros significant. That number has 4 significant figures. This number does not have an explicit decimal, so that zero is not significant. Now suppose we meant to make it significant. Just put a decimal there. Now that rule about orphan decimals doesn't apply for trailing decimals. It only applies to leading decimals. They need to be bracketed with 0. The reason I don't say it for this one is because if we put a 0 out here to bracket that decimal, we've added another significant figure. So we can't do that. So these decimals, they hang out there by themselves. There's nothing I can do about that. So there's a difference. This has 2 significant figures. That one has 3. Okay, there's one other type of number when we're talking about significant figures, and those are exact numbers. They're numbers that we designate as infinite significant figures. So whenever you see them in a calculation, they have no bearing on the answer insofar as the significant figures count. So counting numbers like 9 pencils, in this case, that's an exact number. Or conversion factors, equivalence, where we say 1 inch equals 2.54 centimeters, 2.54 centimeters, and 1 inch for that matter, have infinite significant figures. Now, that doesn't mean anything right now, but when I talk about what to do in a calculation, then it becomes important. But first, we need to tackle one other topic, exponential notation. Now, the authors of the book treat exponential notation the same as scientific notation, and it's not. Exponential notation is a way of expressing large numbers or very small numbers in a more convenient format. So let's say, for example, I have that's big enough. So we want to put that in a form that's a little easier to handle. So one way is to take the understood decimal here and move it, right, to make a smaller number here. But you can't just throw away that information. We've stored away 10, 100, 1,000, 10,000, 100,000, 10 to the 5th. That's exponential notation, but we could also write it and that's the same number. We haven't lost any information at all. This is called the coefficient, and this is the power. Now, both of these are exponential notation because we have a number with an exponent in it, right? Power of 10. And this is only valid for decimal numbers, of course. But this is exponential notation, and that is scientific notation. What's the difference? Scientific notation says that the coefficient has to be between 1 and 10. Right? That one's not scientific because that's 35. It's greater than 10, right? So there are two advantages to writing it this way, and we're going to focus on scientific notation, like that. The advantage is you can write very large numbers or very small numbers in a convenient format. So this is a large number, we did it. Let's make a small number. Like that. So when you move the decimal to the left, you store up positive powers of 10. When you move it to the right, you store up negative values of 10. So 1, 2, 3. There. So that's scientific notation for this number, right? And you can tell anytime you have a negative power of 10, the number's less than 1. Anytime you have a power greater than 10, the number's greater than 1. That's simple. The other nice thing about scientific notation is if you do it right, you can instantly see how many significant figures are in your number. Just count the number here. There's 4 significant figures in that number. Here, there are 1, 2, 3, 4, 5, 6 significant figures in that number. Or you could do it from here, or you could do it from there. But scientific notation is helpful sometimes in that regard. Okay, suppose we have to, let's see, 3 o'clock. Oh, good, I got 45 minutes. Maybe I can finish and maybe I can't. There are 2 sets of rules for calculations, mathematical operations involving significant figures. What do you do with the significant figures in your answer, right? Because everybody knows when you got a calculator running, the calculator is going to give you all the digits you want. It doesn't make that judgment. It doesn't say you can only have this many in your answer. It gives you everything. So you have 2 sets of rules. One is for multiplying and dividing, which is the easy rule, and the other is for adding, subtracting. And of course, multiply, divide. Multiply, divide also has a subset of powers, right? Because powers is multiplying the same number over and over and over again. So it fits in this first rule. Okay, the rule is in this case, when you multiply these 2 numbers, you look at how many significant figures are in the operators, right? 1.342 is 4 significant figures. 5.5 is 2 significant figures. And our calculator tells us the answer is 7.381. The problem is we cannot legally keep all of those significant figures because we're limited by the least accurate one. And that's this one. 2 significant figures limits our answer to 2 significant figures. That's the multiply divide rule. So how do we get there to 7.4? Well, we get this number, which is okay as an intermediate step, but we need to decide how many of these numbers can we keep. From the left, 1, 2. We have to stop there. So that requires that we round. And our rounding rule is we're going to use the simplest one. If it's 5 or above, we round up. If it's less than 5, we round down. So we look just to the right of this number, and that's an 8. Greater than 5, we round up and throw the 8 one out. 7.4 then is the answer. One mistake that I haven't seen very often, but it's good to avoid, is you don't round this one and then that one and then that one, and you keep rounding like that. You only round from the number exactly immediately to the right of the one that you have to stop at. Okay? Now there's the add-subtract rule. In the add-subtract rule, you line up the decimal points, right? So we got these two numbers that we want to add together, and we say like that. Then we add them together, so we get 5, we get 7 here, we get 12 there, carry the 1, we get 4, plus 7 is 11, carry the 1, we get 3. So our first step answer is 31.275. But we're limited to the number of decimal places in the least accurate number above. So we have to stop right here, right? That means we've got to round to this digit. 5 or above, we round it up to 8. That's why our answer is 31.28. Okay? And as always, you guys stop me if you need to ask a question. Okay, now the next possibility is combinations. What do you do when you get a combination of add, subtract, multiply, divide powers in your calculation? Well, if you have parentheses in the calculation, it will give you the order, right? Everybody remembers that from math class, right? If you're not given parentheses, then this is the accepted order. Parentheses first, all right, no parentheses. Exponents next. Right? You know, no exponents, multiply, divide. All right, multiply first, divide next, and then you do add, subtract. But if you have parentheses to guide the steps, then so much the better, because this method will give you one answer, and parentheses might give you a different answer altogether. Okay, now here's a concept. Let's suppose that we want to measure water and combine the two amounts for our experiment. But we only have these two cylinders. One of them is 5 milliliter max with these divisions in it, which each one looks like it's 0.2 milliliters each. And this one, that's 1 milliliter total. That means that each one of these other big marks is 0.1, and in between is 0.02. So which one is more accurate? The one on the right, of course. It has smaller subdivisions. The one on the left is less accurate. So intuitively and qualitatively, how are we limited by these measurements? You're limited by the least accurate device in the sequence. So we're limited by the accuracy of this one. Right? So if we say, this one looks like it says 3 milliliters, or 3.0 actually, because, right, the last one is an estimate. So we estimate that it's exactly 3. So we say 0.0. Whereas this one is 0.3, and it's sitting on 0.3. So we say, okay, we're going to estimate the last one, 0.30. Add them all together. You're limited to this one right here, because it's the least accurate with our add subtract rules. So 3.3 is the allowable reported volume for this measurement. Okay, problem solving. I like to keep things really simple. The authors say, what is my goal? I say, what's the question? When you read, especially if you're taking a test, you read a word problem, or you're reading a homework problem and it says yada, 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 yada. You're looking for the question. What is the question? If you don't know the question, there's no way you can get the answer. Then you say, is the information there that I need to answer the question? Or can I find it legally? For instance, you will always have a periodic table available. And nearly always you'll have some useful information that I grant you during a test. Can I find the information there? And then, once you get the information, how do I organize it to solve the problem? Some problems are really simple, like just simple, straight out calculations. But later on, they're going to get complicated. So what you have to do then is subdivide that question into multiple questions. And the answer of each question gives you information for the next one. Or, other possibility, work the problem here for this half, then combine them and get your final answer. So how you organize your approach to a problem is critical. And it all starts with, what's the question? Because one thing about word problems I've learned, there's a lot of blue smoke there. Whoever made that question is just blowing smoke in your face, trying to confuse you. So that's why these word problems, it's so important to understand the concepts and the methodology for working the problems beforehand. Master it. Like I said, I think I said last time, your two best friends are curiosity and boredom. Curiosity helps you look for information and methods of solving problems. Boredom tells you when you got there. If you work 20 problems, the same type, by the time you get to the 20th problem, you're going to be bored. All right, so curiosity and boredom are your two best friends. Okay. This concept, dimensional analysis, the dimension is the units of measure. Right. What are the dimensions of this room? Well, this room is maybe, I don't know, 10 feet by 15 feet or 18 feet, something like that. When we talk about dimensional analysis, we're basically saying the problem, the solution to the problem lies in the dimensions, in the units of measure. So many problems in chemistry can be solved purely based upon unit conversion. We want to go from one unit to the next to solve the problem. And to do that, to make that conversion, you need an equivalence statement. One or more, actually. So what we're saying is something like this. 1 foot equals 12 inches. All right? So, if we know that, and the question is, what is that value in feet? How do you make the conversion? Well, this is where you start, and this is where you end up. You need something that will allow you to convert that to that. The conversion factor goes in here. And it's designed to cancel that one. Remember when I said numbers, add, subtract, multiply, divide? Units of measure also add, subtract, multiply, divide. So we want to cancel that unit and leave us with this one. So we want this and this in our conversion unit. But in order for this to be equal to that, that number has to be equal to 1. If it's different than anything else, if it's not 1, then that cannot be equal to this, right? Because if you multiply something by 1, it's the same on both sides. If you multiply it by something that's not 1, then it's not equal. Even 0, if you multiply it by 0, you got 0. Multiply by 2, you've doubled the amount, so you're not equal anymore. So we need something that's equal to 1. Well, how do you get it equal to 1? Here's your equivalence. Let's say we need inches on the bottom. So let's divide both sides by the same amount. There we go. Right? In mathematics, if you divide both sides of an equation by the same amount, or you multiply both sides by the same amount, then that's valid. You haven't changed it. It's still equivalent. So we divide both sides by 12 inches. This is equal to 1. Right? That's equal to 1. Now this 1 is equal to that. So this is equal to that. And this is our 1. That's what conversion factors do. Now, since this is equal to 1, right, that means that's equal to that, we can flip it. It's still equal to 1, right? Dividing by, doesn't make a difference. It's still equal to 1. So if we had feet over here and we wanted inches, we just flip that, put feet on the bottom. It's still equal to 1. That's why conversion factors work, because they're always equal to 1. They're derived from an equivalence. Okay, that's what this page says right here, and I'm not going to labor that one any further. On occasion, you may have to use more than one conversion factor. I call it chained conversion. And this concept still holds. We want to make this pounds into this grams. But we don't have a single conversion factor that will take us from pounds to grams, right? Unless you have it memorized, which I do. But in this case, we do know that 1 kilogram is 2.2046 pounds, and 1 kilogram equals 1,000 grams. So if we multiply this one as a conversion factor, right here, convert that into conversion factor, that's equal to 1. Pounds cancel, leaves kilograms. Now we got to get rid of kilograms and leave us with grams. This one converts into a conversion factor equal to 1 and goes right here. Kilograms cancel, leaves us with grams, right? And the reason we can chain those conversions is each one of these factors is equal to 1. And you can multiply something 1 times 1 times 1 times 1 all the way to the end of the world, and you haven't changed it. Not intrinsically. You've changed the unit of measure, ideally, but it's still equal to 1. Now here's a problem-solving question. What information do you need to answer this question? What data would you need to estimate the money you would spend on gasoline to drive your car from New York to Los Angeles? Right, what do you need? What's the question? You're going to drive from New York to Los Angeles, and you want to know how much money it costs. I mean, how much money do you need to take with you so that you can buy gas all the way there, and I might add, if you're coming back, twice that much to get you back? Well, you need some things. You need to, first of all, you need to know how far it is, right? Then how do you convert miles into dollars? Right? It doesn't say that there. So if you have miles, then you want to end up with dollars, right? How do you convert miles to dollars? Well, one conversion factor that would do that, would get you there, started there, would be how many gallons of gas does it take to go a mile in your car? And then what's the price per gallon? That'll get you to dollars. Okay? I used to do this all the time. I've got family in Atlanta, drive from Beckley to Atlanta. I know how far it is. I have a pretty good idea of the price of gas on average between here and there. And I know the mileage, gas mileage of my car. So I can estimate. So I say twice that is the bare minimum. And then I pad it with 10 or 15% for driving around. Okay. We talked about earlier, one of the fundamental units of measure is the Kelvin for temperature, but that's not the only one that we use. In fact, there are no thermometers that I know of, at least I've never seen one, I'm sure they make them, that will spit out a number in Kelvin. And by the way, when you say so many kelvins, you don't say degrees Kelvin. You only say like 300 K. That means 300 Kelvin units measuring your temperature. Whereas Celsius and Fahrenheit always have that little degree mark. Okay, so these are the most common systems. Fahrenheit is typically used in the life sciences or in weather, right? Temperature for weather. Celsius is used in all other sciences, chemistry in particular. And then sometimes you have to convert between the two and convert Celsius to Kelvin. Right? So how do you do that? Well, you need to understand how they're related. Remember when I said that nature just does what it does, right? If it's this certain temperature, it doesn't matter what the scale is. Nature says, this is where I am, deal with it, right? It's either hot or cold or somewhere in between. So we devised these ways of measuring the temperature. And one of the first ones was Fahrenheit. That was a German by that name who was interested in living systems. So he wanted his system to say, okay, 0 degrees is as cold as I can get. So he had saturated saltwater solution in ice, and that's his 0. And then he wanted something that was in the range of a living system. So he said, all right, 100 is, I stick the thermometer in my wife's mouth when she's mad at me. And that's 100. We now know that normal body temperatures are around 98.6. But even that varies. But once he established the 0 and 100, all he had to do was then subdivide it into 100 units. And those were the degrees Fahrenheit. That same thermometer could be calibrated differently, right? That position may go from 0, a chemist came up with this one, Celsius. 0 degrees is the freezing point of water. So any laboratory can duplicate that. All they need is distill water, make ice, mix it with water, and as long as there's ice and water together, it's 0 degrees. And the boiling point then would be way up here, right? 212 degrees Fahrenheit up here would be 100 degrees Celsius. Then he subdivided it. The first thing you notice is that the subdivisions from 0 to 100 in Fahrenheit are a lot smaller than the subdivisions in Celsius, right? So that's a problem for conversion. The other problem is the 0 point moved. 0 for Celsius is actually 32 Fahrenheit. So in order to make the conversion, you have to say, all right, I'm going to take Fahrenheit and multiply it by this ratio. For every 5 degrees centigrade, I move 9 degrees Fahrenheit. Right? But the 0 position moved. So in order to get Celsius, we would also need to subtract 32. And this doesn't show it, but I'll give it to you in just a second. Whereas Kelvin, the 0 point for Kelvin is absolute 0. That is, you can't go any lower than 0 K. So that's why there are no negative numbers in K. And in order to change, I also said that the size of the degree for Celsius was the same as for Kelvin. So here all you have to do is shift the 0 point. So when you have 0 degrees Celsius, you have 273 degrees K. So here's what it looks like. If I want to know, this is the one I memorized right here. If I need to know temperature in Fahrenheit, then I take centigrade temperature, Celsius temperature, excuse me, multiply it by 9/5 and add 32. Right? Your book might say, instead of 9/5, it might say 1.8. Same value. And then once you have this formula, if you know Fahrenheit but you don't know Celsius, then you can stick in Fahrenheit and solve for the unknown. Right? That's why for this course, you need to know algebra. You don't have to know a lot of algebra. You just need to know how to solve simple equations for unknowns. And of course, this is the conversion for Celsius, excuse me, to Kelvin. 273 plus C is Kelvin. All right. Believe it or not, there is a number, a temperature, in both Celsius and Fahrenheit where they meet. They're both the same. So in order to determine that number, you take your formula and say, okay, if this value is equal to that value, then just give them the same unknown, x. So we'll say x equals x minus 32 times 5/9 in this case, and then solve for x. And as it turns out, minus 40 degrees Celsius is equal to minus 40 degrees Fahrenheit. This one is in here to drive home the point that whenever you have an equation, and this is our example, density, whenever you have an equation, there are unknowns and there may be constant values. But when you have an equation, that means density is equal to mass divided by volume on that side. So D equals M divided by V. All right. The thing about this is this is the definition of density. Density equals mass divided by volume. Usually grams and cubic centimeters or grams and milliliters. But it's still an equation. It's a mathematical expression. And if you know any two of those, the third one is a single unknown, you can solve for it. So you can either fill in what you know and solve for the unknown, or you can solve for the unknown and then fill in the values that you have. Works either way. But you always need to pay attention to the units of measure. In this case, grams per cubic centimeter is usually reserved for densities of solid materials, where grams per milliliter is used for densities of liquids and gases. That's just convention. Okay, here's an example. We calculated the density. I need to take a very short break, bathroom break. So I'll be right back in about 3 minutes. Excuse me. Okay, I'm back. Another point I would like to make is when we have a measurement or a calculated value for that matter, we can look at it in terms of whether or not the amount of substance makes a difference in what the value means. And what I mean by that is it can either be a capacity value or it can be an intensity value. Right? Intensity values don't matter how much of the substance you have. It's always the same. So if you have a chunk of silver of, say, this much, or you have a chunk of silver this much, it still has a density of 10.5 grams per cubic centimeter. That's an intensity factor. If we have amount of silver like this, you know, that may be 20 grams. But if we have this much silver, that might be 3 kilograms. That's a capacity factor. Very many capacity factors are single units, like kilograms, meters, seconds, whatever. Whereas intensity is usually a quotient, like density is grams per cubic centimeter, grams per milliliter. But not always. One intensity factor that's very important is temperature. Temperature, as long as the substance is uniformly mixed and distributed, temperature will be the same whether you have this much or this much. Okay? So temperature is a single unit that expresses an intensity factor. All right. So this was an example where we had one unknown. It wasn't density. We already know the density. So the unknown is mass. Right? So we can solve that equation for mass. Okay. Let's see. Just to remind you, if I run out of time officially, and you have to be somewhere at 3:45, go ahead and go. I'm going to keep talking until I'm finished and record the whole thing. So you can finish anything that you have to miss because of other obligations. You can catch it up later. I'm pretty close to the end, but I may run out of time. Okay, how do we classify matter? Well, one way is what phase is it? And what we mean by that, is it solid, is it a liquid, or is it a gas? They all have different characteristics, right? Now, that's not the only states of matter that are available in the universe, but those are the three main ones, and those are the ones that we're really concerned with on the surface of the Earth. So we find that solids are of a definite shape. They maintain their own shape without any external container. and they have a definite volume. Whereas liquids have a definite volume, but they can't hold their own shape, so they need a container. And gases go one step further. They have neither definite volume nor definite shape. They need a container to hold both the volume and the shape. And you put a gas into a volume that's evacuated, and it will expand to fill that space. Okay, and that's what this says. Solid is just that. Liquid's just that, just like I said. No big mystery. Another way to describe matter is in terms of pure substance versus mixture. So, what's a pure substance? A pure substance is something that can be continually divided by physical means, right? Separated until you get to the smallest unit, and all those divided parts are identical. So with distilled water, we can divide it into 2 beakers. Then we can take that and divide it into 2, keep doing that until we get down, theoretically, to 1 molecule of water. We can't divide the molecule of water any further, otherwise it won't be water. Right? So physical separation of a pure substance leaves only the same substance in every division. Mixtures, on the other hand, take 2 or more pure substances and put them together. Right? They can still be separated by physical means and retain their individual identities, but they can't be divided. Once you reach the smallest amount, they can't be divided any further, okay, by physical means. Now, mixtures come in 2 varieties. Homogeneous mixtures, where you put 2 or more substances together and they're evenly mixed throughout. That is, no matter how big or how small, if you take a smaller sample out of different parts of that mixture, they will always be the same composition of the different pure substances that you put together. That's homogeneous. Heterogeneous mixtures, on the other hand, if you take a subsample from one part of a heterogeneous mixture and from a different part, they will have different compositions. Right? For instance, colored jelly beans. Right? If you take a handful of jelly beans in this hand and a handful in that one, and then count the different colors, they'll always be different. Different numbers of each one. Whereas a homogeneous mixture, salt water, you'll have the same composition of salt throughout, or sugar water, same. Or gases. If you mix 2 gases together, it always makes a homogeneous mixture. And has a special name. Homogeneous mixtures are called solutions. So gases make solutions every time you mix them together. And it stands to reason. Gas molecules are very far apart, right? There's room for everybody. So they just mix together and go about their business. Okay, which one of these are homogeneous mixtures? Test-taking technique. Look at the question, which is a simple question, and work backwards. Which ones of these are mixtures in the first place? Pure water? Copper metal? Not a mixture. Gasoline's a mixture. Jelly bean's a mixture. Soil's a mixture. Take my word for it. You shove a shovel into the ground, pull it up, and you can see that there are at least different colors, different particle sizes. Soil is a mixture. So we've narrowed it down. Only 3 of them are mixtures. So we got to figure out which one's the homogeneous one. Right? Take my word for it also. Soil is not homogeneous. It's a heterogeneous mixture. Jelly beans, I just described them as heterogeneous. So the only one left is gasoline. Gasoline is a solution of different components that you blow through your engine and burn. All right. Now we've skipped one thing here. We skipped properties. There's a difference between properties and change. Change requires something to happen, something to go from here to there. Property is a static description or a description of potential. Like if we say that paper is flammable, right? That's a chemical property. But if we say paper changes from this substance to ash and water and carbon dioxide in the presence of air, that's a chemical change. Same thing for physical, except that with chemical changes, bonds have to be broken. Molecules have to be ripped apart. Whereas a physical change only separates individual molecules or ions or atoms. The physical change takes a substance and separates its components, its parts, by physical means only. That is, the individual molecules, individual atoms, if they are there, the individual ions are separated, but no bonds are broken. So that would be a physical change, and we can do that in various ways. Well, let me back up and go back to properties. We talked about chemical properties. Now, physical property is a description of the substance in terms that do not allow breaking of bonds. So let me illustrate. When we say the boiling point of water, the boiling point of water is 100 degrees Celsius. That's a physical property. A physical change with that similar reference would be we distill water from the salt by boiling it. That requires a physical change from one phase to another. So the water in the mixture, the solution, the salt, uses the chemical property, uses the physical property of boiling and the boiling point to effect a physical change from liquid water to gaseous water or steam. Okay. Various other types of physical changes are possible, and they're based upon physical properties. I just mentioned distillation. Right? So we can distill water from salt by boiling it, and then if we condense it, we get water, pure water. But it's always been water, whether it was in the mixture with salt or whether it was pure distilled water, it's still water. So we did not change the identity of the substance. So we can also describe these in terms of upon what physical property does this change hinge? And the physical change of distillation hinges upon the boiling point. Okay? Filtration, for instance, is a requires a physical change, and the physical property is particle size. Particle size of a substance does not change its identity. It just makes the particle smaller or larger, as the case may be. But the physical change is based upon that physical property of particle size. Chromatography is a little more difficult to explain. The interaction of the substance, for simplicity, let's say it's in a liquid. So we've got a mixture, a solution actually, a large amount of a certain substance, and then a smaller amount of something like maybe a colored substance. And if we dip a piece of paper in that solution and watch the solvent front, the solution, try to move up the paper, what we may see, if there's more than one color in there, is we may see those colors start to separate. The physical property that allows us to do that is called adsorption. Not absorption, AB, but AD, adsorption, which is a surface phenomenon. In other words, those colored chemicals in the mixture are attracted to the paper. But they're both, say we only have two colors. Each color is attracted to the paper differently. One of them is more strongly attracted to the paper than the other one. So what happens is it attaches to the paper for a split second, and then it goes back into solution and moves up, and then it reattaches. And the strength of attraction to that paper, which is a physical phenomenon, a physical property, is different than the other color. So the amount of time in each cycle that the more strongly attracted one spends will keep it lower than the less strongly attracted one, and they separate. That's chromatography. Paper chromatography, to be specific. Okay. So here's that chemical change that we mentioned earlier. If we actually change the identity of the substance, then we have undergone, the substance has undergone a chemical change. So methane is in your Bunsen burners in the laboratory. And when we strike them, we've added air to the methane in the natural gas, and the reaction takes place in which the natural gas and the oxygen interact. Bonds are broken and reformed, and we have new substances on the other side, plus heat. That's a chemical change. And it's based upon the chemical property of methane to combust in air. So let's see if we can identify which one of these is a chemical change. Pulverizing rock salt. What has happened? Ask yourself, is it still salt before and after the process? That's obviously a physical change then. Burning wood. Is the substance identity different before and after? Yes. Wood is a different substance than the ash and the water and the carbon dioxide that comes out the other end. So that is a chemical change. Dissolve sugar in water. Okay, we have table sugar in our measuring device. We put it in water. What happens to it? Well, we could say it changes chemically, but you'd have to prove it. So how would you prove it? Well, you have to remove the water. See if you can get the sugar back. And in fact, if you evaporate the water, you get the sugar back unchanged. That is a physical change. Melting a popsicle on a warm summer day. The melting popsicle does not undergo any chemical change. It still has its identity. The icy water along with the coloring and the flavoring and everything, are still there. So none of those components have changed their identity, which means it's a physical change. Okay, this is a decision chart, a flow chart for deciding what you've got in your possession as matter. So if it's a pure substance, then it always has the same composition, right? Because there's only one substance in there. If it's a mixture, then maybe it's homogeneous or heterogeneous. If it is, then they can be separated by physical means. If it's a pure substance, then the only way that you can acquire parts of that pure substance is through chemical change. You have to break and possibly reform bonds to form new substances. Now, if the pure substance happens to be an element, then you can continue to subdivide the pure substance, and you'll always have element. And of course, that's a physical change. So you get physical changes over here, definitely, and you could possibly have a physical change over here when you're separating a pure substance into individual atoms. That's a physical change. But if you have to break bonds, if the pure substance is a compound, then the only way that you can change it any further is through chemical means. Okay, so now that's the last part of the video that was interrupted by the freezing of my computer. And now it's up to me to put Humpty Dumpty back together again.